Good morning, good afternoon, and welcome. We're so glad to have you here at our webinar, How to Build a Quantum Computer. And this details a project that Tabor Electronics and FormFactor did over a period of about 12 months last year that we highlighted at the American Physical Society March meeting last year. My name is Mark Elo. I'm going to be the moderator and the host for this webinar. I've got 30 years of cross-functional test and measurement experience in instrumentation. I was a design engineer in Hewlett-Packard's microwave division, and I've held various management positions in Agilent Technologies, Anritsu, Gigatronics, Tektronix, and Keithley Instruments in both research and development, sales, and marketing. I've got an honours degree in solid-state electronics and an MBA. So we built a quantum computer, but what does that mean? Why would a bunch of engineers, with the help of some physicists, do this? Well, the first step in making a quantum computer is to have it available for all levels of education. So far, a quantum computer has been something that's been in a lab, it's been handcrafted, it's had some custom parts made for it. So how can we do it so it becomes more of a turnkey, out-of-the-box solution? And the market now is asking for a quantum workforce. So how do we train that quantum workforce? And there's more smaller scale labs coming online. So how do we reduce the cost of entry for small research labs as well? And above all, we really wanted to simplify purchasing, supply, and installation of such a product. And yes, it is a product. It's built by manufacturing companies, and it's not an experiment. So we set ourselves some goals. One of the main goals was we want to base this thing on complete industrial standards, limit the custom hardware. And so everything had to be off the shelf or open source. So when you look at industrial standards, what does that mean? Well, we wanted cross-vendor instrumentation compatibility, and we wanted to follow as many international standards and be in compliance with them and be compliant in all our manufacturing capability. And when I talk about off the shelf, what that really brings to us is economies of scale, because we're not only making this equipment for the quantum community or a quantum computer community, we're making it for multiple different markets. So we can make many hundreds or many thousands of products, which really reduces the cost with making, and this is a key contribution to making a quantum computer available for everybody. And then open source, we want it to be shareable, non-proprietary, no specific vendor lock-in with respect to software systems. Today, if you buy an electronic control system or some quantum computing subsystem, you really get tied into a specific vendor, and then it's very hard to increment or innovate or add more capability to experiment. So we wanted to keep all that as flexible as possible. And the specifications that we challenged ourselves with was exceed the T1 time of 100 microseconds, have it for less than $1 million to buy, and with less than 1 year delivery. So those were the goals, and you'll see how we achieve that as we go through the slides. We built the Echo 5Q, and this is a commercial endeavor between FormFactor and Tabor Electronics, and we chose to use the QuantWare QPU and traveling wave parametric amplifier. FormFactor, they supplied the dilution refrigerator and the main system integrators for this project. Tabor Electronics, we provided the control electronics and the characterization software. And from QuantWare, they provided a very stable chip to us, a 5-qubit QPU, and we also used the QuantWare traveling wave parametric amplifier on our readout lines. Just a brief introduction to the QPU from QuantWare. It's called the Soprano. It's a 5-bit QPU. We also use the Crescendo as our traveling wave power amplifier, but both of these were very easy to use. They're pre-packaged. You order them, they just come off the shelf. In the quantum world, they provide excellent value. The cost point's not too high, and of course they've made a few of these now, and so we've got a lot of metrics on reliability and performance that we could rely on. So when choosing the QPU for this project, it seemed like a natural path for us to go with QuantWare. Let's take a look at the systems overview. So we split the system into room and cryogenics. So on the room side, we use the Proteus arbitrary waveform generator from Tabor. We use the Lucid high frequency signal generator as a Tupa driver. And we also use the Yokogawa GS200 DC sources for the flux bias line control. On the cryogenic side, the heart of the system is the FormFactor HPD LF600 fridge. And as I already talked about in the previous slide, we put the Soprano 5-bit QPU in the bottom of the fridge, and then we use the Crescendo S as our traveling wave parametric amplifier on the readout lines. Let's talk about the control electronics. The heart of the system in the room temperature is the Tabor Proteus P9484M arbitrary waveform transceiver. Now, this is an FPGA-based direct digital synthesis system that goes up to 10 gigahertz. It's essentially a 4-port arbitrary waveform generator and a 2-port analog to digital converter with 9 gigasamples and 5.4 gigasamples of sampling rate, respectively. It's got all the FPGA code that you need inside it for onboard averaging and demodulation, and it's available in multiple form factors, including a 19-inch rack version and the PXI, and it conforms to the PXIe industry standard. For the Tupa driver, we use the Lucid 4-channel LS1284R synthesizer. It's a high-performance signal generator. It's got frequency ranges up to 3, 6, 12, 20, and 40 gigahertz. We're using a 12 gigahertz model here, and Jin will talk about the resonant frequencies as we go on. It's got pulse modulation, so we get high isolation, i.e. we can turn the output off and get about 90 to 100 dBs of isolation. Again, it's available in a 19-inch rack with PXI, and there's a PXI industry standard module available as well. Now, all the modules go in our chassis, the PXE 21100 chassis. So this is a chassis that's been specifically designed using the PXI industry standard, but modified slightly for quantum physics applications, especially quantum computing. So it uses the industry standard backplane. It's compatible with multiple types of instruments. So you could buy a PXI DC source if you wish. You could buy a lower frequency arbitrary waveform generator and plug it in. And it just provides a really flexible plug and play architecture. And why did we choose Proteus as our quantum control system? Well, at the heart of the system is a programmable FPGA, and then we use that programmable FPGA to drive RF DACs and RF ADCs. So if you look at the RF DACs, each RF DAC has an IQ modulator in it, so we can generate pulses and change the pulses and tune them to different frequencies, transmit that signal looking on the right-hand side of the screen, and then we can receive or do the readout with the RF ADC running at 5.4 gigasamples. That goes into acquisition memory, and then within the programmable FPGA, we can do some post-processing, digital down conversion, averaging, and also we have what we call decision block architecture in there. So once we receive a signal, we can make some decisions on what is the next signal that we want to play out. For very large pulse sequences or very large quantum programs, if you will, it has up to 16 gigasamples of memory. So we can play out many, many millions of different types of waveforms, depending on what type of pulse sequence that you want to do. Our open source software is actually called LabRad. So this is open source, as I said, and it's originally developed by the Martinez Group at UC Santa Barbara in the physics department, and a version of it was adopted by Google. They've made many iterations, of course, in Google, and it's a custom system, but we've chosen to use it because it's open source and it's available to anybody, and it provided just a very easy to use and very self-explanatory platform to allow other people to be able to program our quantum computer. And what we did was modify it to take advantage of some of the modern control electronics, such as our Proteus instrumentation, which is not just an ARB, it's not just a signal generator, it's not just an oscilloscope or digitizer. It's all of those instruments bundled into one and then really optimized in terms of its operation to provide a good quantum computing control system. At the bottom of the screen, you can see that there's an example here of one of the methods for doing a Rabi scan. So you can define your scan range, scan type, number of averages, the loop sequence, and so on and so forth, all in a single line, and out will pop the appropriate results that you're looking for. And there's a number of these, and Jin will touch on it in the third part of the presentation and show you some of the results that he obtained using this open source software system for doing our Qubit characterization. So the schematic, the basic control schematic, is pretty straightforward. So we have the Qubit at the bottom of the refrigerator, and then we have the one Proteus doing the Qubit drives on qubits 0, 1, 2, 3, 4, and 5. And then on the readout side, and Jin will go into more details, we have another arbitrary waveform generator providing the right resonant frequencies to do the readout, and then we use our digitizer to take the readout and interpret that into the specific measurement that we want to do. And the readout schematic, going into more details, so we provide a pulse sequence or a pulse to do the readout. And you can see it's a multiplex readout line looking at the bottom of the slide. Duplexer, we have the lucid providing the signal, the microwave signal for the wideband tupa, and then that's amplified, and then amplified at a slightly lower temperature, and it goes out to the Proteus to perform the actual readout. I'd now like to introduce Joe. Joe brings over 20 years of experience to the team. Along with his deep technical knowledge, Joe's experience extends to account and product management with sales and marketing roles at Lakeshore, Cryogenics, Oxford Instruments, and Agilent Technologies. Joe's got a degree in physics from Michigan Technology University and a doctorate in condensed matter and materials physics from Kent State University. Joe was our main partner at FormFactor. And Joe, would you like to tell us a little more about the cryogenic side?
Okay, thank you for that introduction, Mark. So as Mark mentioned, FormFactor was the chief system integrator, and everything was integrated on our LF600 dilution refrigerator. This is a lab scale quantum system for dilution refrigerators. This is a 300 millimeter mixing chamber plate. And you can see there's 2 line of sight ports that enables up to 54 RF lines. So while we did a few qubit measurement here, this could easily be expanded to a 25 qubit measurement in the same system. Obviously, anything for quantum measurements, you want a dilution refrigerator with the lowest temperature and highest cooling power, and that's what this is. So you can see this is 600 microwatts at 100 millikelvin and 20 microwatts at 20 millikelvin. I'll expand more on those details, but the most important thing is that you obviously want cooling power at the lowest temperature. The way we did that is by improving the dilution refrigerator core, and I'll talk about that on the next slide. Part of a dilution refrigerator is dilution refrigerator core. This is the part that actually does the cooling. So what we did in our system in this LF600 is a new dilution refrigerator core. So what we're here from the bottom, looking at the mixing chamber, step heat exchangers, an ICP plate, continuous heat exchangers, and the still. This is an all modular design, and it's all using modern manufacturing techniques. So obviously a dilution refrigerator needs the best heat exchangers, and that's what we did when we streamlined the silver sinter process to make the step heat exchangers. So these are very efficient heat exchangers. Everything is laser welded and basically a repeat reliable manufacturing process. Nothing is handmade. There are no solder joints in this. Everything is kind of a repeatable design, and it's a very efficient dilution refrigerator core. I'm showing it kind of an expanded view and also the view inside the LF600 fridge. I'll show you some results in a second, but not only is it a modular design, but there's because we can expand upon it, we can make a system with larger cooling powers or even lower base temperatures. So these are the results. So I kind of alluded to before, but the system got down to less than 5 millikelvin. So you can see we're actually around 4.7 millikelvin. So a very strong dilution refrigerator core. Like I said, 600 microwatts at 100 millikelvin. And probably more important for any quantum measurements is the cooling power at 20 millikelvin, which is where the measurement was done. And so you can see this is actually like around 20 microwatts at 20 millikelvin, which is a large amount of cooling power in a relatively small fridge. And I don't have it listed here, but I say it's very efficient with the helium-3. It's only like 23 liters of helium-3, which is kind of world-class in the efficiency to get cooling powers and base temperatures at this level in this size of a system. So to make a quantum measurement, it's more than just getting the lowest base temperature and high cooling power at 20 millikelvin. You also want a relatively quiet system. Quiet meaning minimize thermal load, minimize infrared interference, and a magnetically shielded environment. There are a couple unique features in the LF600 I want to highlight. One is the 10K plate. So if you count up stages, mixing chamber, ICP, still 4K. There's this 10K plate in between the 4 and the 50. This is important because there's actually some cooling power there you can take from the pulse tube. And this is important because you're putting RF lines down and you can intercept the heat at the 10 Kelvin stage. Intercepting heat at the lower temperature is always a win. And because you have this 10 Kelvin plate, you can also put amplifiers there at both 4 Kelvin and 10 Kelvin stage. So it gives you a little extra flexibility and ability to intercept the heat. The other nice advantage of the new DR core is that the ICP stage is actually running much colder than probably other stages. So this is about 85 millikelvin. Why is this important? Because again, you can intercept the heat at a lower temperature. We're running lots of RF lines down. The RF lines are bringing a heat load. Even though we got lots of cooling power, we don't want to use too much of it on dealing with the heat load of the coax lines. You would love to intercept the heat at a higher temperature stage. And if you can intercept at the ICP stage, and the ICP stage is 85 millikelvin instead of 100, that is a huge win in terms of heat load at the mixing chamber. In addition to those type of thermal issues that the fridge enables, there's also an IR black coating in the mixing chamber shield. So I'm looking at the outside of the mixing chamber shield in this picture, which obviously shields from higher temperature stages, but the inside is coated black. So it's very absorbent to any infrared. So obviously minimizing any infrared radiation that could interfere with your measurement. The whole system is light tight as well. And then you can see probably a better picture here is the magnetic shielding of the whole system. So you can see both the 5-qubit device and the TUPA are shielded in the open system as well. So that's kind of a quick overview of the dilution refrigerator we use for this. So I'm going to hand it back to Mark, and he can introduce Jin and talk about our results.
Thank you, Joe. That was very interesting overview of the dilution fridge. One of the biggest takeaways I got through this project was your ability to keep the fridge at a constant low temperature, no matter how much microwave energy the Tabor instrumentation brought down into the QPU itself. So thanks for that, Joe. Now, Jin is going to talk about the results and the measurements. Jin is a skilled experimental physicist with expertise in quantum control and operations, particularly in the development and optimization of 2-qubit gates between superconducting qubits. He has a Master of Science degree from Peking University and a PhD from Erlangen University in Germany. He later moved to the US and worked as a postdoctoral associate at MIT. And then after that, Jin joined NIST, the National Institute of Standards and Technology, where he worked first as a physicist, and till this day, he is a guest researcher there now. Jin works for Tabor Electronics, and he's our chief quantum scientist. Jin, would you like to talk to us about the experimental results?
Thanks, Mark, for the introduction. So I guess so far we have seen how the system looks. So it's like a brand new car, and my job is to bring you to have a test drive. So on the right side, you will see the diagram of the 5-qubit chip with the 2 extra qubits for sanity checks. All the readout cavities are sharing the same readout line, for the blue line from top all the way to the bottom. If you choose one of the qubits to investigate, you will first, of course, do the readout cavity specification and find the cavity there or resonator there, and then you do the spectroscopy of the qubits, and then you will see one peak. Then each of the qubits has a dedicated flux line there, which using which you can bias the qubits. And this is a very tedious work to change the bias very carefully and record the change of the qubit frequency. But this, luckily, we can automate. So on the left, you can see the 2 qubits spectroscopy versus their DC bias. And you can see the points are really dense, and this is actually automated. It's done overnight with just one press of the key on the computer. So once you see those qubit resonances, you can proceed to do the Rabi oscillation. On the left, you can see T-Rabi is actually pretty long. It is above 100 microsecond, which is a very good sign. And also, of course, you can see in the middle, if you tune the drive frequency, you will see the classical Rabi chevron. The next thing is to do the T1 and T2. So by T1, we apply pi pulse and wait, and then do readout. T1 is above 100 microsecond as well. The T1 is pretty long across several qubits on the chip. Also, we did a T2 star, the Ramsey experiments. It is also pretty long, above 100 microsecond, which is indication that our system is really light tight. It is not exposed to stray photons that will kill your T2 star. If we do a echo experiment, you will see T2 echo is actually not much longer than T2 star. So it is only increased from 100 microsecond to around 120 microsecond. This is also a good indicator that we are not suffering from the low frequency noise. Of course, it is still a little bit away from the level of 2 times T1, but there it seems the noise is mainly from the high frequency. The next thing we did is a single qubit randomized benchmarking, which is the tool to show how many pulses we can apply to how many qubit gates we can apply to the one single qubit before it decays too much. The result is pretty good. So we easily can go above 3 nines. Right after the calibration, we can get as high as 99.96% fidelity. But once you are above 3 nines, everything matters, and it will slowly drift away from the optimized point. And but if you take a long time to measure, the fidelity is still going to be hovering above 99.93%. I need to emphasize that here we didn't apply any drag or any automated calibration tools. I'm pretty sure with those tools applied, we can push the single qubit fidelity to even higher level. Here, I also want to emphasize that when the designer designed the chip, they have this traditional method to move the qubit frequencies around so that they match each other. In that sense, in that way you can induce the 2 qubit interactions and realize a controlled Z gate, which has been out there for more than 10 years, I believe. And this time, the QuantWare reported that they can achieve 99.7% fidelity on that front. But this chip can actually do more than that. So here, I have 2 examples to show you. First, you can try to induce the so-called cross-resonance interaction, which is driving for example, driving the green qubit 2 in the middle through the drive line of qubit 0. And the drive strength will depend on if qubit 0 is in ground state or excited state. Here on the left, you can see the Rabi frequency is different depending on the state of the qubit 0. This is the cross-resonance interaction. If you fine-tune it, you can get a cross-resonant gate, like to make it a C0 or something like that. The other more fancy thing is you can drive the qubits difference frequency between qubit 0 and qubit 2. So on the left, you can see a chevron. It looks like a Rabi chevron, right? But it's actually not. It's a little bit dim, but on the x-axis, you can see the drive frequency is in megahertz. So 300 megahertz, this is roughly the difference of frequency difference between qubit 0 and qubit 2. By driving that difference frequency, you can actually create a swap between EG and GE. Therefore, you can get your own iSwap gate or CZ gate if you choose to drive at a slightly different frequency. This is known as a parametric interaction or parametric CZ gate or iSwap gate. What I'm saying is here is actually this system has a lot of potential, and it's a very interesting project to investigate. So to summarize, if you condense everything to a data sheet, then this system has a T1, T2, and T2 star, all above 100 microsecond, which is a pretty decent number in the industry. And the single qubit gate fidelity can be easily above 3 nines, and 2-qubit gate fidelity has been realized to be above 99.7%. Readout fidelity, which I didn't emphasize much, but this is also reported by the QuantWare, the fab company, to be above 97.5%. This shows that the 2-pi is really working well. And the single qubit gate duration can be shorter than 14 nanoseconds, but we find the optimized length is at 14 nanoseconds. On that note, I'll return the stage to Mark.
Thanks, Jin. Those results look amazing. And I think we're all very proud at both FormFactor and Tabor Electronics of what we were able to achieve with the QuantWare chip or QuantWare QPU. So to conclude, what you can see is that when you see the system and its performance, you're not buying an experiment, you're buying a machine to perform experiments. And, you know, we've achieved this all with off-the-shelf technology. You focus on the manufacturing and the integration processes and the repeatability, and you can get this type of performance and make it available at a lower cost point. These full stack systems are starting to enter the early production phase, and we're going to even continue to drive down the cost of a system like this, and they're going to make it easier for even smaller universities that want to start their own quantum computing facility, or industrial organizations that want to have them in a training lab, for an example. This is going to be able to provide this access to this technology for more and more people. And as Joe said, we've also built the system so it's expandable up to 25 qubits as our logical next step, using the same hardware. So with that, I'd like to thank you all for listening, and now it's your turn to speak, and we're going to open it up for questions. Thank you.
Let's have a look at what we've got. So, this one looks like it's for Jin. It says, what is limiting the qubit coherence, Jin?
Hi. For T1 time, it is pretty clear that the fabrication is the limiting factor, so material science. So there are defects on the chip, and across the board on different qubits on the same sample, we have almost identical Q factors for the qubits, so which means it is the material science that's limiting the T1. For T2, there are a few factors. First, because T2 star is already slightly longer than T1, it's clear that T1 is mildly limiting the T2. One other factor is likely the that the resonator is not empty, which has maybe a fraction of a photon in the resonator, which in turn changes the qubit frequency, and that's another. I think it's currently the main limiting factor of T2. It's not just to make it light tight, but to make the resonator very, very cold, which is still challenging. Thank you.
Thanks, Jin. Another question. I think this one came in a couple of times. I think this one might be for Joe, but what's the cooldown time and warm-up time as well?
So the cooldown time for the fridge, and I'll just add there was like about 13 RF lines on this for this experiment and others. The cooldown time's on the order of about 24 hours. Similar warm-up time as well for this fridge.
All right, thanks, Joe. And you actually just answered another question that came in as well.
Yeah.
How many RF lines? So that's good. What is the max gate speed? I think, Jin, this is another one for you. What's the max gate speed in the current configuration?
For a single qubit gate, with the amplifiers that comes with electronics, you can do 20 nanosecond single qubit gate or even faster. The question is if that deserves the effort, because if you go that fast, you have to really be careful not to induce more errors in the process. So currently the best the sweet spot, if you would, is around 30 nanoseconds for single qubit gates, where you get the best fidelity. For 2-qubit gate, it strongly depends on what kind of 2-qubit gate you want to induce. For the traditional on resonance CZ gate, the speed is limited by the static coupling between the 2 qubits, which is around 20 to 30 megahertz. In turn, you get around 40 nanoseconds of 2-qubit CZ gate. That is the speed.
Okay, thanks. And I think, Joe, this could be another one for you or Jin, but we talked about RF lines early, but another question is, in total, i.e. probably when we get up to the higher qubit counts, but what's the total amount of lines, flux lines and bias lines that the fridge can host?
Okay, so if we just keep it like low density SMA connector lines, the fridge can do 54 RF lines, which is not going to get you to 25. However, there are flex lines, high density connectors. And like I said, the fridge has 2 ISO 100 ports. So at a low density filling factor, that's like, 54 RF lines. But at high density, we could easily double that. And that doubling gets you in the order of 100 RF lines, which is easily achievable with high density lines. And that would be what you would need for 25 qubits approximately. For 25 qubits, you need approximately close to 100 RF lines. So, and that would the wiring would all fit. And then the heat load is really not that much for this fridge.
Okay, and bias lines, like the DC? The low frequency
DC,
stuff?
you could easily put lots of DC and, multiple twisted pair looms, easily fit 4 or 5. So there's plenty of room for DC lines.
Fantastic.
Hey, Mark, I see 2 questions in the Q&A. 2 new ones I'd like to quickly answer. So first, the type of qubit is transmon. Yes, they all the qubits. For the sample I show, 5 out of the 7 qubits are flux biased. So yes, you need flux lines to bias them. The other one is for the automated code. Unfortunately, we do not publish the code publicly on GitHub.
Yeah, not yet. But it's I think we'd like to encourage you to talk to us rather than just take the code. Piggybacking off the quantum, is that the one that you just answered, Jin?
Sorry, which one?
This question's from House of Fries.
No.
Piggybacking off can you see it?
Yes, I can see it. For the here the question is it purely is the coherence purely a material problem or a architecture or a topography problem? Currently, the Purcell limit is way higher than the T1 time. So at the same time, in the society, I believe everyone is investigating the material problems, especially making some progress when you swap in new materials. So I don't have exclusive conclusion there, but I strongly believe it is still a fab problem. Yeah.
Okay, and then one last one. I think this could be Joe, but it's looks like more NMR. What provides? Do you provide setups with superconducting magnets for spin cubic setup?
The short answer is yes. Probably get into the details of what magnet you need for that, but yes, the fridge can support a magnet or whiteboard magnet that would be used for spin qubit measurements. So we probably get into it offline, but the short answer is yes.
Okay, let me just check this chat box, see if there's any more. I think that's it. So I'd like to thank everybody for attending this morning. We had a wonderful time explaining and showing off the work that we've done in the last year. It was a fantastic project, and we're going to continue to work on it, expand it out to 25 qubits or more, depending on what technology we can get our hands on. If it's in the open source market or it's for sale as a product, we're always interested in integrating it into our test system that we have over in Boulder, Colorado, and then seeing how we can productize that as we go forward. So please, if you've got anything you would like to contribute to our system, or you are interested in the system itself, contact any one of us, or contact Tabor Electronics or FormFactor through the usual reach outs on their websites, and we'll send you a follow-up email to ask you how much you enjoyed our webinar, and then that would be a good place for you to start an interaction if you choose to. So thank you, Jin. Thank you, Joe. Thank you, everybody. And visit our websites, formfactor.com and taborelectronics.com to learn more. Thank you all. Have a great day.